In this episode, we take a careful look at what it really means to protect data while it is moving between systems and while it is sitting in storage. Many new learners hear phrases like data in motion and data at rest and assume that the solution is simply to turn on encryption everywhere and call it done. Encryption is important, but it is only one layer, and it can be undermined if storage controls are weak, if access is too broad, or if key ownership is misunderstood. The practical security question is not just whether data is encrypted, but who can access it, how it can be copied, how long it persists, and what happens if an attacker gains a foothold. Protecting data requires thinking about boundaries, identity, and recovery, not just algorithms. The goal here is to build a clear mental model of where data is exposed, how controls reduce risk, and why ownership of encryption keys often determines who truly controls the data. A strong foundation starts with definitions that are simple but precise. Data in motion refers to information traveling across networks or between processes, such as when a browser talks to a web service, when an application calls an internal service, or when files are uploaded and downloaded. Data at rest refers to information stored on disks, in databases, in backups, in archives, or in any persistent storage location where it is not actively moving across a network. The reason these categories matter is that the threats and the controls differ, even though the same data may shift between these states many times. Beginners often imagine a single location where data lives, but real systems create multiple copies and multiple paths. A report might exist in a database, be exported to a file, be emailed, be cached, and be backed up, meaning the same sensitive content appears in many forms. Protection starts by admitting that data travels and multiplies, and then designing controls for both movement and storage. When we talk about protecting data in motion, the core security goal is to prevent interception and tampering while information traverses networks you do not fully control. The most common protective mechanism is Transport Layer Security, TLS, which provides confidentiality and integrity for traffic between endpoints. The important nuance is that TLS protects the link between 2 points, like a user and a web server, or one service and another, rather than creating universal end-to-end secrecy across every hop by default. If traffic passes through intermediaries, terminates at gateways, or is decrypted for inspection, the trust boundary moves, and you must be clear about where the data becomes readable again. Another beginner misunderstanding is assuming that encryption in motion automatically proves identity. In practice, identity is proven through certificates and trust validation, and failures there can lead to secure-looking connections to the wrong party. So the right mindset is to treat in-motion protection as both a confidentiality layer and an identity-checking layer that must be kept intact. In practice, protecting data in motion also involves controlling where data is allowed to travel and under what conditions. Even if traffic is encrypted, sending sensitive information to an unintended destination is still a data loss event, because encryption does not fix a wrong recipient. This is why secure design pays attention to allowed connections, trusted destinations, and careful handling of endpoints that can receive data. It also means thinking about segmentation, which is the idea of limiting which systems can talk to which other systems, so that sensitive data flows only along paths that make sense. Segmentation is often described as a network concept, but it is really a data movement concept, because it reduces the number of routes data can take if a system is compromised. If an attacker compromises one machine, they should not automatically be able to reach every database or every internal service. In-motion protection is therefore a blend of cryptography and traffic discipline, where encryption protects the content and segmentation limits the possible paths. Data at rest protection begins with the reality that storage is both a convenience and a liability. Stored data is attractive to attackers because it can be collected in bulk, analyzed slowly, and monetized over time, and it is often easier to steal large amounts from storage than from a live network stream. Storage controls are the first line of defense here, meaning permissions, access boundaries, and strong authentication around who can read, write, and export data. Beginners sometimes assume that storing data behind a login makes it safe, but storage systems often have multiple interfaces, multiple roles, and multiple ways to access content, including administrative access, service accounts, and backup systems. A practical control mindset asks, who can access this data directly, who can access it indirectly through applications, and who can make copies through exports or reporting. The more paths to storage, the more you need consistency in enforcement, because a single weak path can undermine all stronger paths. Encryption at rest is a powerful control, but it is often misunderstood because people confuse encrypted storage with unreachable data. Encryption at rest means that if someone steals the physical storage media or gains low-level access to stored files, the content should be unreadable without the corresponding key. This is extremely valuable for protecting against device theft and some forms of unauthorized storage access. However, it does not automatically protect against an attacker who compromises an account that is authorized to access the data through the application, because that access will often decrypt data as part of normal operations. In other words, encryption at rest reduces risk when storage is accessed outside the intended pathways, but it does not eliminate risk when the intended pathways are abused. This is why encryption at rest should be paired with strong access control, monitoring, and least privilege. The beginner-safe conclusion is that encryption is a harm reduction layer, not a permission system, and it must be treated as part of a larger control design. A major reason encryption can fail to deliver its promised protection is key management, and this is where key ownership becomes a central concept. When data is encrypted, the key is the thing that makes the data usable again. So whoever controls the key effectively controls access to the data. If an attacker obtains the key, encryption becomes a speed bump rather than a barrier. If an organization cannot access the key when needed, encryption becomes a self-inflicted denial of service. Key ownership is therefore not just an administrative detail, it is a security boundary choice. If keys are controlled by the same system that stores the data, a compromise of that system may expose both data and keys together. If keys are controlled separately with tight access policies, an attacker may need to break two different controls to get readable data. This separation is one of the most important ways encryption becomes meaningful rather than cosmetic. Key ownership also matters because it defines trust relationships between organizations, vendors, and internal teams. In many real-world environments, data is stored in services that are operated by someone else, even if the data belongs to you. If the service operator holds the keys and can decrypt the data, then your confidentiality depends on their controls, their policies, and their incident response discipline. If you hold the keys independently, then the operator may store and process encrypted data without being able to read it, depending on the design, which changes the trust model significantly. Beginners often assume that using encryption automatically means the service provider cannot see the data, but that is only true if the provider does not have access to the keys. This is why key ownership discussions often become sensitive and sometimes political, because they determine who can comply with subpoenas, who can access content for troubleshooting, and who bears responsibility in a breach. Security is not only about what is possible technically, but also about who is allowed to do what operationally. A practical way to think about key ownership is to separate three roles: key creators, key custodians, and key users. The creator role determines how keys are generated and whether the process is trustworthy and auditable. The custodian role determines where keys are stored, who can retrieve or use them, and how rotation and revocation are handled. The user role determines what systems can request cryptographic operations and under what identity and authorization checks. When these roles are blurred, human error and overbroad access become more likely, because a single person or system may have the ability to create, store, and use keys without oversight. When roles are separated thoughtfully, the system becomes more resilient to mistakes and to insider abuse. This is not about making everything slow. It is about making it harder for one compromised identity to unlock everything silently. For beginner learners, the key lesson is that encryption strength is meaningless if key custody is sloppy. Protecting data in motion and at rest also requires attention to how data is copied, cached, and backed up, because those are common pathways where controls drift. A system might encrypt a database at rest, but then produce daily exports that are stored in a less controlled location. An application might use encrypted connections, but then write sensitive content into logs for debugging. A collaboration workflow might store files securely, but users might download them to unmanaged devices for convenience. These are not rare edge cases. They are normal behaviors in busy environments. This is where data loss prevention, DLP, thinking becomes useful because it focuses on where sensitive data tends to leak during normal work and how to guide users and systems towards safer behaviors. The main idea is to protect not only the primary storage but also the shadows, meaning the copies and derivatives that appear through routine operations. If you ignore shadows, you create a false sense of security that breaks the moment real work begins. Monitoring is the control that ties everything together because it helps you detect when data protection assumptions are being violated. Monitoring does not mean reading everyone's content. It means paying attention to signals that indicate unusual access, unusual movement, or unusual volume. For data in motion, this might mean noticing unexpected destinations, spikes in outbound transfers, or patterns that suggest bulk extraction. For data at rest, this might mean noticing unusual reads, sudden permission changes, or access from identities that do not normally touch sensitive repositories. Beginners sometimes think monitoring is a luxury, but it is often the difference between catching an incident early and discovering it months later. Monitoring also helps validate whether controls are actually working, because you can see whether data movement stays within expected boundaries. In security, you rarely get perfect prevention, so detection becomes a core part of protection rather than a separate concern. It is also important to understand that access control and encryption need to be designed with the human workflow in mind, because otherwise people will route around them. If secure storage is too hard to reach, teams will create informal storage. If sharing rules are too strict without an approved alternative, people will use personal accounts or ad hoc methods. If key access is so restricted that operations cannot recover during incidents, someone will eventually create a hidden backdoor path for emergencies. These outcomes are not signs that users are bad. They are signs that the system was designed without enough empathy for how work happens under pressure. Protecting data on purpose means designing controls that provide safe, usable paths for legitimate needs while still making risky behaviors harder. The best controls feel like guardrails, not obstacles, because they keep people moving forward while preventing the sharpest mistakes. When you design this way, you reduce both the probability and the impact of data loss. Another critical piece is understanding how identity compromise changes the meaning of both in-motion and at-rest controls. If an attacker steals valid credentials, they may access data through legitimate channels, meaning encryption is not directly challenged because the system decrypts data for authorized users. This is why strong authentication, least privilege, and continuous evaluation matter so much, because they determine whether an attacker can turn stolen identity into broad data access. It also explains why session security and access control topics connect directly to data protection. A protected storage system is still vulnerable if the accounts that can access it are weakly protected or overly privileged. Beginners sometimes see cryptography and identity as separate topics, but in reality, they are intertwined. Cryptography protects channels and storage, while identity decides who can use those channels and storage legitimately. If identity is weak, cryptography becomes a secure wrapper around insecure permission decisions. Finally, protecting data in motion and at rest requires a mindset about recovery and resilience, not just prevention. Even with strong controls, mistakes happen, credentials get phished, devices get lost, and systems get misconfigured. Resilience means having the ability to restore data when availability is compromised, to rotate keys and re-establish trust when key material is exposed, and to contain incidents so they do not spread. It also means knowing where sensitive data lives, so you can answer the most painful incident response question quickly, which is what was exposed and what was not. Controls like backups, audits, and key rotation plans are not afterthoughts. They are part of the protection story because they determine whether an incident becomes a minor disruption or a lasting disaster. When you protect data on purpose, you build the assumption of failure into your design, and you plan for fast, disciplined recovery. That is what turns security from wishful thinking into operational capability. To close, protecting data in motion and at rest is about more than turning on encryption and hoping for the best. In motion, you need strong encrypted transport like TLS, but you also need clear trust boundaries and controlled pathways so data does not flow to unintended destinations. At rest, You need storage controls that enforce least privilege and reduce unauthorized access. And you need encryption that meaningfully reduces harm when storage is exposed. Key ownership is the practical determinant of who can actually read protected data, which is why key custody, separation, and lifecycle discipline matter as much as algorithm choice. You also need to account for copies, backups, logs, and normal work behavior, because that is where data protection often fails in the real world. When you combine storage controls, encryption, and clear key ownership with monitoring and resilient recovery planning, you create a data protection posture that stands up under pressure instead of collapsing during the first real incident.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.